So now you already know how to identify acid, base, salt, and covalent. You know which ones are soluble in water, and you know what the difference is between a strong acid and a weak acid, and a strong base and a weak base. We can now look into this and see what happens when these are dissolved in water. What do we actually see in the water? What particles are present? And our major focus here is going to be, are there molecules or ions present? And which one do we have more of if they're both? Now we're going to look at solutions and electrolytes. For the moment, let's focus on the particles present in the solution. We'll be looking at covalent compounds, salts, acids, and bases. Each of these classes of compounds behaves differently when they dissolve in water, and so we're going to look at each one closely for the rest of this video. Before we continue on, I'd like to remind you of how we model some of these particles. First, we're going to look at covalent compounds. When it's a covalent compound, that means they are linked together by a covalent bond. Covalent compounds can be nonpolar or polar. A nonpolar compound would have the two ends that are the same, so there'll be no polarity, and we'll model it like this, with two of the same colored ball. A polar compound will have two different ends, so we're going to model that with two different colored balls, and I'm going to show it with a delta positive and a delta negative to show that they are a partial positive and partial negative on the molecule. We're going to draw an arrow above it to show which way the polarity goes. The positive part is on the more positive part of the compound, and the negative part is on the more negative part of the compound. When we look at an ionic compound, again, we'll have two separate particles. They'll be joined together with an ionic bond. So we're going to have a positive charge over here and a negative charge over here. And these ones are going to be fully charged, so we're not going to put that little delta sign in front of it. So full positive, full negative. That's an ionic compound. Notice that it's difficult to tell the difference between a polar covalent compound and an ionic compound. They're very similar to each other, but in an ionic compound, those charges are completely separate from each other, whereas in the polar covalent compound, there's still some sharing of electrons. When first looking at this, you may have a hard time deciding, is this a polar covalent compound or is it a ionic compound? Because they look very similar. Since they both have two different ends, they should be the same. But notice that in the covalent compound that's polar, they're still sharing the electrons. In the ionic compound, they are not sharing. One is giving away the electrons, the other one is taking the electrons. The major place that we see a difference between these polar covalent compounds and the ionic compounds is when they dissolve in water, and that's why we're focusing on that in this section. Notice that in these molecules, I'm only using two particles. That's just because it's simpler to draw, so I could, of course, have a much larger covalent compound that is completely nonpolar or completely polar, but we're going to model it in this way just to make it simple to draw. And the last bit I want to add to our models is water. While water is just a polar compound, I'm going to model it this way so that you can see there's a positive end and a negative end to water, and I'm showing all of the atoms. And finally, let's draw that arrow in for water to show which direction the polarity lies. Let's start with covalent compounds. We'll start with this covalent compound made of one yellow and one green ball. This is a molecule, as covalent compounds are molecular compounds. But of course we don't see the single molecules, we see them as a collection of those known as a compound. Here you can see that we have a collection of those molecules stacked together. When we add that to water, let's see what happens. As you can see, we still have the molecules left. They're just not joined to each other. But what's important to note is that in the dissolving process, we still have 100% molecules left. We started with molecules, we finished with molecules, they're just now separated from each other. Notice that this molecule must be a polar molecule to be soluble in water. So we're going to model that with a partial positive on the yellow part and a partial negative on the green part, and see what happens when it dissolves in water. Notice that the water will surround this molecule, but it doesn't break it into pieces. So it will surround the particles, but it doesn't separate the particles. Notice that the positive end of the molecule is surrounded by the more negative parts of water, and the negative end of the molecule is surrounded by the more positive parts of water. But they are not separated from each other. It stays a polar molecule. And the key point here is that covalent compounds do not separate into separate atoms. They stay as molecules, but each molecule is separated from the other molecule as they're surrounded by the water molecules. And that's what we call solvation. Now let's see what happens when we dissolve a salt. For example, let's look at sodium chloride, which is composed of a positive sodium ion and a negatively charged chloride ion. Again, when we find them in nature, we'll find them as a collection of these, known as an ionic compound. Now let's see what happens when these dissolve. We can see that both the sodium ion and the chloride ion are separated from each other, and they are surrounded by the water molecules. The main thing to note here is that we get 100% ions when an ionic salt dissolves. Now let's see what happens when an acid dissolves. To start off with, an acid is a covalent compound and it's polar. So what happens when a polar covalent compound dissolves? We use hydrogen chloride as an example of a strong acid, and we'll start by drawing the collection of particles in this beaker. Since strong acids are a type of polar covalent compound, when a strong acid dissolves, it first separates into its separate molecules. But where a strong acid is different from other covalent compounds is that it goes through another step which is called ionization. This ionization process occurs immediately upon contact with water. So the very first thing it'll do is separate into its molecules, but then it immediately breaks into separate ions. And we get 100% ions if it is a strong acid. So we're going to see in the water that we have 100% ions in water for strong acids. Now let's look what happens when we have a weak acid. And we'll use HF as a model for the weak acid. We'll start by drawing them as a collection of those particles. Now let's see what happens when we add water. Since we know that these are polar covalent compounds, the first thing they will do is to separate into their separate molecules of HF. And now we'll see the difference between the strong acid and the weak acid. In the case of the weak acid, only a small fraction of the weak acid will ionize. In fact, less than 50% of it will ionize. In this model, we're going to show it as 25%. So of the 4 HF particles we have here, only one of them will break into its ions. So what do we have in the solution? Well, we definitely have less than 100% ions, and we have mostly molecules, but we do have a few ions in there. So the way that we'll write this is mostly molecules with a few ions. So again, this for all of the acids, it's a two-step process. Step 1 is to dissolve the molecules, and step 2 is to turn it into ions. In the case of a strong acid, it goes 100% and gives us 100% ions. In the case of a weak acid, it goes less than 50%, and so it gives us less than 50% ions. So we say a few ions, and a lot of molecules will be found dissolved in the water when a weak acid is present. And finally, we'll look at solutions of bases. Again, there are two classes of bases. We have our strong bases and our weak bases. We'll focus on the strong bases first. For example, we can look at something like sodium hydroxide, one of the strong bases. We'll start with our model. We have our positive charge and our negative charge for the hydroxide. Again, I'm drawing it as a single ball, even though it is a polyatomic ion. I'm just showing it as a single negative charge. And since this is a compound, we'll show it as a collection of those particles. And now I'd like to add water to it. See what happens? We add water, you'll notice that it becomes completely ionized. So strong bases are 100% ions, as we saw with the strong acids. In this case, though, they are 100% ions because they were already ionic. They didn't dissolve and then ionize, they were just ionic originally. And our final grouping is our weak bases. In this unit, there's only one weak base that we consider. There will be some future ones. When we get to Unit 4, you'll see some more weak bases, but you won't have to do any of the observations, figuring out if things are strong or weak or anything like that, but you will see some weak bases, and they are based upon this weak base. Remember, our weak base is ammonia, which is NH3. It is sometimes written as NH4OH, and I'll show you why now. So to start with, NH3 is a polar compound because it has the nitrogen and 3 hydrogens. It is a polar compound. It is a covalent compound. And to simplify this model, I'm going to squish it down so that we have our positive end and our negative end, as we've seen before, to show that it is a polar covalent compound. And since it is a compound, we'll put it all together to make a collection of those molecules. And now we're going to add water to it and see what happens. Because this is a polar covalent compound, the first thing we will see is that it dissolves in water and it separates into its separate molecules. So it's separated by water, just like all of the polar covalent compounds were. Now in the case of the weak base, it's going to ionize, just like our weak acids and strong acids did. It was covalent, and now it ionizes, it forms ions. And those ions are the ammonium ion, NH4+, and the hydroxide ion, OH-. Now how much does this weak base ionize? Again, it's going to be less than 50% of it ionizes. That's why we call it a weak base. That means that in this container, we have mostly molecules with just a few ions. As we saw with the weak acids, we will always have mostly molecules with a few ions. You don't need to know the number. Sometimes it'll be 20% ions, sometimes 30% ions, sometimes 5% ions. It doesn't matter what the number is. We just know that it is mostly molecules and a few ions. So let's summarize what we find in water when these substances dissolve in water. We'll start with polar covalent compounds. We're only looking at the polar ones because the nonpolar ones do not dissolve, so they have nothing in the water. When we look at a polar covalent compound, it starts off as a molecule, and after dissolving, it is still 100% molecules. When we look at solutions made of salts, so salts dissolved in water, we see that those start off as 100% ions, and they end up as 100% ions. When we look at solutions of acids, we have to look at them more carefully because they go through a process called ionization. They start by dissolving and then they ionize. So we look at strong acids, and we know that by definition they ionize 100%, and so that means that they start as molecules, but they become ions, and they are 100% ions when they are in water. In the case of weak acids, we know that they start off as molecules, but then when they contact water, they become ionized. But in this case, they are less than 100% ions. So what we are going to see is that for weak acids, they are mostly molecules with just a few ions present. And finally, we look at the bases, and most bases are ionic to begin with, and those are our strong bases. And so those ones will be 100% ions when dissolved in water because they were already ionic, they stay ionic. And now we have the challenging one, and that is our weak base, ammonia, also known as ammonium hydroxide. And that one starts off as molecules, it becomes ionized, but less than 50% ions, and so we see that it will be mostly molecules with just a few ions. And what you need to focus on here is whether substances will have molecules, ions, or mostly molecules with just a few ions in the container. That'll help us determine some of its properties.